In this practical, we will try with some simple simulation and estimate heritability for simulated data. So you need a desktop or laptop and are installed in your machine, and also you need a library mass and Excel file. And course material for this practical can be downloaded from this website that include R code and some Excel file. So I can so if you when you go to this directory, I will show you. Yeah, then you can, if you go the address, then you can find some link under the title population analysis using statistical genetic tool. Then you can click, then the materials can be downloaded to your machine. So I already downloaded. Then I will show where is, yeah. So I use Mac, so the system looks like this, but probably Windows or other platform also similar. Or you can use probably Putty or other Cwin or any other application. So I already made so where this folder is. So this is where I downloaded and unzipped the file. Actually not. Sorry. Yeah, so this one. This folder I downloaded the file and unzipped. Then you can find some R code. So in this practical we will use this code and also these two codes. So make sure that you have this R code in your folder. Okay. Then now we can ready to go. We are ready to go. So first practical using the VG that represent the genetic variance, and SIM is a simulation. So this is a simple simulation for genetic variance and residual variance, and some of them is phenotypic variance. So first question is what is phenotypic variance? Before going this practical, we can have a look what does the code looks like. So we can have a look. So the code name is VZ. Yeah, so library mass is for multivariate normal distribution simulations that used in somewhere here. I will explain soon. Then here the simulation number of record is 10,000. Then number of trait is 1 at the moment. Then the mu is the mean that I show in the lecture, that normal distribution, then the middle of the distribution is actually mean, right? That's mu. Then it all set as a 0, assuming the variables are mean centered. Then this is a true simulated value that genetic variance is set as 5 and residual variance set as 12. Then this is how to simulate genetic values. So I give a name as a GV, genetic value. So this is our function, that's normal distribution, as Tn, the number of records. So I will simulate 10,000 records as a mean 0, that is here, mu 0. Then variance G is 5. So in R code, the function R norm requires standard deviation rather than variance. So this will give 10,000 genetic values. And exactly same function, then we will also simulate residual variance that I assign as EV. So same number of record and the mean is 0 as well, and the variance is come from the residual variance here, that's 12. Okay, then according to the equation P equals G plus E, so here I assign as YV, that's phenotypic value, and GV is genetic value, and EV is a residual value. So this is actually phenotypes. So from these phenotypes, you can work out the phenotypic variance, right? So also you know the genetic value as well as the variance, also residual value and residual variance. So it is straightforward to get the phenotypic variance and genetic variance, therefore heritability. Okay, so we can run it using R. So this is the same folder as here. Then I will run R. Then so in R function, the source is one of the make the code run. So I will, so that's VZ, right? So we call VZ, then it run. So from the one replicate based on this simulation code, that is this one, the phenotypic variance is around 16.9 and genetic variance is around 5 and heritability is around 0.291, right? So let's have a look at what is the question. So sorry, yeah. So what is phenotypic variance? So we already so the phenotypic variance is around 16.9, right? Easy. That's easy. Just then what is the genetic variance? There is genetic variance here, 4.95. And what is, so we can see, so what is highest value for the genetic value? So what is the highest value for the genetic value? So we can see the maximum and minimum value. Also, first maybe we may have looked at histogram. So we can draw histogram from the genetic value. Then something like this, right? So the maximum value is around 9 and minimum value is around -9, right? So this is normally distributed, mean as 0. That is what we simulated. Also, genetic variance we simulated as 5. So this around 5 is one standard deviation, as I show in the lecture, right? Then this is a distribution of the value. Okay, so the answer is maximum value of genetic variance is 7.8 and minimum value of genetic variance is -9. Okay, and next question, yeah, we did. Then what is expected heritability and what is observed heritability? So from the simulation, we assigned as true simulated value for the genetic variance as 5, right? Then residual variance is 12. So what is expectation? That is genetic variance divided by genetic variance plus residual variance, right? So the expected heritability is 0.294, okay? Then what is observed heritability? That is 0.291. right? They are very similar. Okay. Then the question: why the expected heritability and observed heritability is slightly different? This is because we use the stochastic simulation. That's why there is a sampling error that depending on the number of record. Okay, so if this record is smaller, then the difference is larger. If this number is large and goes to infinity, then expectation and observation is closer and closer. Okay. Next question is no, this. Okay, so we have done that this one. So yeah, next question. This is about genetic correlation. So although we didn't really mention genetic correlation, but in the simulation we can have a briefly look how to simulate two correlate traits. Then let's have some practical on that. So first we look at the VG dash sim2, and this is very similar to the single trait. Only difference is now number of trait is assigned as 2 here. Now 2 trait. Then the mean is the same as 0 as before, and genetic variance for the so in this case this is a second trait. So first trait we assign as 5 and 5 for the genetic variance and 12 for the residual variance. Now for the second trait we give a genetic variance is 200 and residual variance is 500. Then the correlation between first trait and second trait. So in this case, actually genetic correlation, and probably residual correlation is 0. According to here, I will show in the next few lines. So this function a bit complicated, but this basically saying that this is the first genetic variance, and this is correlation times square root of genetic variance for the first trait and second trait. It means this is genetic covariance, and this is same as this one, and this is second genetic variance, right? So this is basically shows. I will probably give sorry, I'd like to find my whiteboard. So yeah, here. So I can briefly draw what does the structure look like. So first I will delete this one. So the line basically has a 2 by 2 structure, genetic variance covariance structure. So this is the first trait, this is the second trait, and this is the first trait, and this is the second trait. Then the code actually specify the genetic variance for the first trait here, and genetic variance for the second trait here, and this is the genetic covariance, and this is the same. There is a symmetric variance covariance structure. So this is the same as this one, this one. Okay, so this code basically specify the structure that I show here. So in this case, the correlation times square root of the first trait and second trait for genetic variance is actually genetic covariance. Okay, so this variance covariance structure is stored in GMAT, that is genetic structure matrix. And how do I simulate genetic value? I use now multivariate normal distribution. So using 10,000 record as before, and using mean as 0, and using the structure specified here, right? Then it will give a multivariate normal distribution for that genetic value. Then residual value here is the same as actually before in the single trait. That means there is no covariance structure. Okay. Then phenotype. This is simulated as before. The phenotype is genetic value plus residual values. Okay. Then let's run this code. So using same source, and second tree. Okay. Yeah. So as you can see here, this YV is not single vector. This is a kind of matrix. That is a number of records by 2. That is the first trait and second trait. So there is a correlation between the first trait and second trait for the phenotypes. And this is a correlation between the first trait and second trait for genetic value, right? So in this code, it shows the phenotypic correlation is 0.1 and genetic correlation is 0.3. So, so this is the answer for the question. So what is phenotypic variance structure? And what is genetic covariance structure? And what is expected genetic correlation? And what is observed genetic correlation? So you can also have a look from the actual value. So this is a function that gives structure for the value. So that is something like this. So this is a phenotypic variance structure, right? This is the genetic variance plus residual variance for the first trait, and this is for the second trait, and this is covariance. So, and what is genetic structure? That is GV. So this is the genetic variance for the first trait. This is genetic variance for the second trait, and this is genetic covariance. So you can probably you can check whether according to this code whether that is agree with this observation or not. So what is expected genetic correlations? So because you simulated the true simulated value is 0.3, right? So expected genetic correlation is 0.3. This is for genetic correlation that you simulated, right? So this is 0.3. Then what is observed genetic correlation from the data? So this is around 0.32. It's quite close, right? Close, but also it's in the same principle. So that depending on this number of records. If this number of records is very small, then this difference can be large. But if this record is getting large, then expectation observation is getting close. So in the previous practical, you used heritability equal actual genetic variance divided by phenotypic variance. Then you got the estimated heritability and compared to the expected heritability, right? But in real situations, you cannot observe actual G. So you need a family design that I showed in the lecture, right? So from the design, then you know what is sample correlation from the design, and you can observe phenotypes. Therefore, you can estimate phenotypic correlation. So from the design, you can estimate heritability from this equation. So let's have a look at the code in the ship-sim-r. Look at this. Yeah. So probably before you start, probably you want to change the total number of SIP pairs. In this case, SIP pairs is 1,000, 10,000. Then probably your code, I don't know what value in your code, but you need to change any value to the 2. So assume you have a 2, one pair of from each family. That's what this simulation does. So let's go through this code. So we simulated heritability as 0.3. This is true simulated heritability. And sample correlation, first we give 0.5. So this is like a full SIPs or digit twins. So from this, we know what is true heritability, right? That's what we simulated. And sample correlation is 0.5. So this is just to compare your estimation and true heritability. So and now we now making design. So the total number of SIPs in the sample is 10,000, and number of members within each family is 2. So like twins, right? So digit twins. Then the mean of phenotypes assigned as 0, and you give heritability for the genetic structure. Then covariance between two SIP pair is function of heritability and sample correlations, right? And this is a symmetric matrix. Therefore, this and this is the same. And also the second digit, the twin, also has the same heritability, right? And this is assigned as genetic structure to here. Then genetic value is simulated from multivariate normal distribution. This is number of record, and this is the mean, and this is the genetic structure according to this code. Okay. Then residual values. Now that is 1 mass heritability, right? This is residual. So in this case, phenotypes are standardized, mean 0 and variance is 1. And for the residuals, there's errors. Errors shouldn't be correlate between SIPs, right? That's why this is assigned as 0. And this is residual is the same as the first and second, the digit twins or the full SIPs. Okay, now this is the residual structure. So this is a residual structure. And EV, there is a residual value. It's come from multivariate normal distribution. This is the number of record, and this is the mean, and this is the residual structure here. Okay. Then the phenotypes is according to the equation V equals G plus E. So that is the sum of genetic value and residual value. Okay. Then so because you can now from the simulated data or real data, you can observe phenotypes for the first and second digit twins or full SIPs. Therefore, you can estimate phenotypic correlations, right? And also because you know sample correlation, there is 0.5 as assigned in the simulation code. Therefore, this phenotypic correlation divided by sample correlation is heritability. Okay, that's what this code is working. So we can try with this code, give a source and give the name, then try. So as we simulated, true heritability is 0.3, and sample correlation, because we design as full SIP or DZ twins, that's 0.5, and phenotypic correlation from the simulation Y1 and Y2 is 0.166, and this divided by this, the sample correlation is 0.333. So this is estimate heritability from this design, right? Does that make sense? So and this within this bracket, this is kind of confidence interval because all estimation has the standard error as well as 95% confidence interval you can estimate. So this shows the confidence interval. Let's briefly have a look how to get this confidence interval. So how does it? So that is from the yeah, this function. That is correlation dot test. Then from the coefficient from this function actually give 95% interval. That is from this. Okay. So first question is what is mean value for the phenotypes for the first SIP. So we can simply give a mean and y v dash 1. This is for the phenotype for the first mean, right? Then that will give close to 0 as expected. That's what we simulated. Also probably it's the same, very similar for the second SIP as well. That's close to 0, right? Then what is the variance? So let's have a look. The variance for the first SIP is close to 1. Is that what you simulated? We can check it out. So easy one. Yeah, because we simulate the genetic value according to the genetic structure. The variance is heritability, right? Then also residual is 1 minus heritability. So sum of this one is 1. That's why phenotypic variance is close to 1. Did that make sense? Also for the second C has similar, right? That's 1. So let's have make a histogram for the first C. Give a hist yv1. Where is histogram? Yeah, looks like this. So this is a mean 0 and the variance is 1 around here. So this is around 1 standard deviation interval. So this is variance. It looks like this. Okay. So also you can have a look what is the maximum number for the y1. First the SIPs phenotypes, that's 3.6. What is the minimum value of the, that is minus. Then also this is 10,000 record for each SIP, but you can probably comparing the first 10 record. Sorry, the other way around. So 1 to 10. Yeah, so this is the first SIP and this is the second SIP. Then so you can see this is from first to 10th family, and first twins, digit twins, and second digit twins. So actually the phenotypic correlation is correlation between this vector and this vector, right? So you can do correlation y1 to y2. So this is phenotypic correlation, right? Then this divided by, because you know these two vectors sample correlation is 0.5. So divided by sample correlation give the estimate heritability, right? That's what you show before here, okay, with this confidence interval. So this confidence interval actually include the true heritability, right? 0.3 is between here. So the estimation is quite unbiased given that the confidence interval. Okay, I hope now you are confident to how to estimate heritability from a full SIP design. So we can go next. So in this case, the question is simple. So you get the phenotypic correlation around 0.166. Then if the pair is MZ twin, then what is heritability? And similarly, if the pair is full SIP, what is heritability? That is what you did here, right? And if the pair is half SIP, then what is heritability? Can you work out? So your phenotypic correlation is fixed, as we assume. Then previously we used full SIP or BZ twins, right? Then that divided by sample correlation as 0.5. Then this gives heritability as 0.333, right? And now, what if the design was MZ twins? Then you scaled by 1 instead of 0.5. Then what would you guess? Would the estimatability is increased or decreased? Let's have a look. So now heritability is decreased, right? Then what if this is half SIP? Then when half SIP, then the sample correlation is now decreased at 0.5. Then heritability goes up. That's 0.66. Okay. So design is important, and the estimate heritability is depending on sample correlation, right? So if given phenotypic correlation, the same value for the phenotypic correlation, then if you use design as a lower sample correlation, then you get the higher heritability. Did that make sense? So we go next. Yeah, then so with the same code, except now heritability goes to 0.8 and run it. Okay, so we can run. So we use the source code, code names. Okay, so we simulate through heritability as 0.8, and we used full SIPs, and now phenotypic correlation is increased from the previous, right? That would be expected because when you use high heritability, then the phenotypic correlation can be increased. That is a function of heritability as well as sample correlation, right? Then now the heritability, estimate heritability is 0.76. So this is a confidence interval, and it includes the true heritability, right? So estimation is pretty accurate, but it's just covered by confidence interval. But if you can increase the this number of SIPs, then probably this confidence interval is reduced, and you get the more accurate estimations. Maybe we can try, or you can try by yourself. So as same as before, also you can work out what is using design as MZ or full SIP. That's what you did here. And what if the design is based on half SIP? Then you can get the different number of heritability, right? Okay, then now get back to the point 3 as before. Then goes to next questions. Yeah, so this is same question as before, right? So now sample correlation change 0.25. So 0.25 is 0.25 is for the half SIP. Then we already have done that, right? Then probably you can do by yourself how they change. So you can get familiar with the design and what design used and how can you estimate, and what is sample correlation and what is heritability, then how you get it. So you'll get, hopefully you get make sense about this approach. Okay, then yeah, now this is about the power, or in relation to the confidence interval. So in the code, let's go have a look. This code, and what if when you change this number of record as 100? So at the moment, yeah, let's try based on full SIP design. Let's try the number of record for the SIP as 100, then to see what happens. Okay. Okay, can you see? So true heritability is 0.3, and we used full SIP design. Now phenotypic correlation is around 0.02, then divided by 0.5 will give around 0.04. This is quite far from the true value, but the confidence interval is huge, from minus 0.3 to 0.4. This actually includes true value, but this is a huge interval. So the estimation, the precision is not that high, right? So that is expected because you used only 100 record. Now what if you try with 10,000? Okay, now the simulated value is the same. Then now the estimate heritability is quite close to true value, right? And confidence interval is very narrowed down, right? From 0.28 to 0.35, right? So it's very close to true value. Maybe you can try with more number. Let's try probably 100,000 million. Okay, then yeah, then it's very close to 0.3, right? Then confidence interval is only 0.001 or something. So this is really high, enough power that close to true values, right? So in design, it is important in terms of power. So that number of record is very important. Okay. So the next question. Yeah, so this is related to confidence interval. Probably, hopefully, you can do by yourself following this question. So you can repeat 10 times for A and 10 times for B, then work out what is the mean and variance of the estimation. So you can run each of these analysis 10 times, then you get the 10 sets, 10 different value for estimate heritability for this, right? And also when you do 100 record, also you get the value for this. Then you get the mean and also variance. That is a function of probably confidence interval. So hopefully you can do the 10 replication then to see how they distributed. That should be interesting. Okay. Yeah, so from this exercise, so we can conclude that the sample size is one of the key factor to determine the accuracy of estimation. Okay. Yeah, so now let's plot the phenotypes for the first SIP and second SIP. Then we can do plot. Let's yeah, we probably you need to change from millions to 10,000. That I already have done that. Then we try again for the simulations. Okay, then now plotting the first SIPs and second SIPs. Then the plot looks like this, right? I wonder what is correlation between this y1 and y2. Ah, that is 0.15, right? So here is it. So this plot is correlation of 0.15. That's not that much, right? So now also we can change probably heritability maybe higher from 0.8. Then try again. Yeah, now its correlation can be increased, right? Then next we get back to heritability the same as before, and we change probably sample correlation as 1 like MZ twins, and try again. Yeah, then also compared to the first one, then it also correlation is increased like this, right? That is also shown in this value compared to 0.15 increased to 0.3, right? And yeah, then we also have whether that affect. So we get back to the full sieve again. Then now we change the number of record. Then try it. So now it's reduced. So it's flooded. Yeah, something like this. There is number of record. But in this case, the phenotypic correlation compared to the first one, there is 0.15. So it's not much different. Actually this is a high sampling error, large variance, right? Based on also this CI. So sometimes it gives 0, sometimes it gives 0.3. It's a lot fluctuating, but the mean should be similar to this. So what can you conclude from this exercise? So this correlation is increased when heritability increased or sample correlation is increased, right? But this is not the mean of the correlation is not affected by number of record. But this confidence interval is affected by number of record. However, this confidence interval is not relevant to the heritability or sample correlation. Did that make sense? Also, probably we can check. Let's have a look. So we goes to get back to 10,000. Yeah, then whether using 0.3 or let's say, so this is when we use 0.3, then now we increased heritability 0.8, and to see what happened. Can you see what is complete interval? So this is around, we can do 0.3 minus 0.5. So this is the interval of the CI, right? Complete interval, that's around 0.07. How about in this case? What is when heritability increased, then this interval is really changed or not? Actually, not much change, right? So it's quite similar. Also, maybe you may have give a very small value, 0.1, to see what happens. Then you get minus, yeah, that is 0.07. So these two values, a slight difference, but it's not much changed. So this standard error or conflict interval is robust against changing heritability. However, sample correlation, that probably I would guess robust as well. Probably you can check by yourself. Okay. Okay, then now in this code, siblings R, can you guess what is Sn? This value Sn, and what is if you change Sn equal 5? Then what does it mean? Can you estimate heritability with Sn equal 5? Can you estimate with this with different number? For example, you can change as 3. Then try. It doesn't work, right? It doesn't work. That is because, so this Sn is actually the number of members within each SIP. So I can draw in the whiteboard. I delete this. Yeah, so you have from the full SIP design or MZ design. So you have the SIP, the first SIP, and this is the second SIP, and this is family 1 to the family n, right? So you use the 10,000 in your simulation code 100 or millions before. So this is the number of record. So you have y1 to the yn. Actually, this should be first record for first SIP y11 and last record for first SIP yn1. You can call, and this should be 1, 2, first record, second SIP to the last record for the second SIP, right? So what you did, get the phenotypic correlation between this one and this one. So that is phenotypic correlation. We can call RP, then divided by the sample correlation between first SIP and second SIP. So in the case of full SIP, you can divide by 0.5. That's what you did to get heritability, right? But now the question is, what if there is more than 2 in one family? So in full SIP or half SIP, that's possible, right? Now this is y 1 3, sorry, this is y and 3. Then how you can get a phenotypic correlation using these 3 informations? Probably you can ignore this information, but then you lose some information that is available, right? That's not what you want. You should use all information available. Then what can you do? So that is the question from this slide, right? So in this case, uh, yeah, in this case that each family has different number of members, and also in each members that is possible uh, that some family has more number, like some family has like 4 or 5 members within family, but some family has only one record available, but this is not is always missing, something like this. So this is not balanced, right? From the different SIPs, some are available, some are not, some are missing, but the other family, they are all available. So this is unbalanced design. So in this case, or number of members in one family is a lot more than 2, then what can you do? Also, in more complicated situation, probably there is complex pedigree. Then what can you do? That is question in the probably in general case. So in the case, so there is a linear mixed model, so that can be used for this problem. Then when you use a linear mixed model, there is some key function, for example, probability density functions or likelihood. So that will covered in the next lecture or practical. Thank you very much.